I think we might be live now.
Exciting.
Let's see if it turns up on YouTube. Let me start my screen share. Yeah, we're live on YouTube. We will start in 5 minutes, 3 minutes for everyone who just started watching. So you can already write your questions in the chat, and I'll start the introduction in a few minutes. And do you just want to say a word so you can do the sound check and see if the audio is working?
Sure. Testing. 1, 2. Exoplanets are great.
OK. Yep, works. I hope that I didn't make too much echo by playing the audio on my phone, but it should be fine.
That's all right.
Yeah, for our regular viewers, you probably noticed we are testing a new setup today. So you're getting here we are using Zoom to stream the meeting, the whole thing, and hopefully that's easier than my previous OBS setup.
Very exciting to be your guinea pig for this.
Welcome, Astrox Physics. Do you? Yeah, now I see the comment.
I don't see any comments or anything like that. I don't know.
There's one message in the YouTube chat now. If you like I don't have the comments in the screen share now this time, so I will just read them out. Or you can go on the YouTube channel, YouTube/Cambridge University Astronomy, and watch it yourself if you want. But I can do it. It's fine.
Okay. Might just.
Should have told you this before we go live, but
sorry.
I should maybe have told you before we go live.
All right, it's a new setup.
Yeah. Also, for those of you who do not have a YouTube account or would prefer to send the questions anonymously, you can go to sli.do and enter the code astronomy to find our event, and then you can use this platform to ask questions. And they should appear on my screen, and I can answer them.
Yeah, we can try to answer.
OK, welcome everybody to this week's Ask an Astronomer episode. My name is Stefan. Today with me I have Andy, and we are going to answer all your questions about science, astronomy, and everything. For that, just type your questions in the YouTube chat or in the Slido, so sli.do and #astronomy, or in the Periscope chat. Yes, I can see Periscope comments. Thank you for the test. I didn't know it would work, but it does work. I can see them. And I will read out everything and make sure that Andrew gets to answer questions. And now, do you want to introduce yourself and say a bit what you're working on, what you want to be asked about?
Sure. So yeah, my name's Andy. I'm a second-year PhD student at the Institute of Astronomy. So what do I work on? Well, so I'd put it like this: when a star like the sun dies, it will still have a load of planetary material orbiting it, which can be planets, it could be asteroids or whatever. If that falls into the atmosphere of this dead star, you can kind of see the signature of its, so it will sort of pollute the atmosphere. And you can sort of measure the ratio of different elements relative to each other. And from that, you can try to learn about whatever the planetary material was that fell into the star. So that's what I'm attempting to do.
That's very cool. Okay, so someone who is an expert about, in particular, dead stars, well, and dead planets. Well, okay, that was maybe the best phrasing. I'll leave that to you.
They are, I mean, basically dead stellar systems. So it's sort of a snapshot of what our solar system might look like in like 5 billion years.
Okay, okay. Yeah, so let's start with the first question on YouTube, which was from Astrox Physics about, is it important to have a finder scope on a telescope? Because I don't have one. Did you ever use a telescope in that way?
Not really. I don't really.
Yeah, so
do much observing. I don't know if do you?
Not professionally. This summer I used my telescope to kind of look at a few kind of double stars and stuff like that. I actually didn't have a kind of so in telescopes you often have kind of a secondary small kind of telescope on top that has a much lower magnification, so it makes it easy to kind of search for a certain object before pointing the telescope at it, because you have a much wider field of view. And I don't think it's that important. Like, as I said, I never used a telescope with one, so I don't really have a comparison. But I did manage to, kind of by looking what direction you approximately have to point the telescope, and then moving it a bit up and down and left and right, I usually managed to find the object I wanted to look at. So I think it's nice to have, but it's not necessary. And while we're getting more comments, in the meantime, I will go and take some of the comments that we got from our big Ask Me Anything a few weeks ago, because we still didn't get to answer all the, 500 comments, so I might just drop in a few of those. I'd love to know how cosmologists and astrophysicists are trying to advance the SETI project, SETI, however, Search for Extraterrestrial Intelligence. Do you know if any of our people in our institute working on this? I don't think so.
I don't think so. I think SETI is kind of viewed as a bit of a, I don't know, fringe might be the right word, like
yeah, let's say it's not mainstream to work on, I guess.
Yeah, so I think that's the right word to use. So
yeah,
in terms of like listening for radio signals or whatever,
I mean, if there would be a radio signal, we probably would still notice it. Recently, there was this big discovery of those fast radio bursts, which are actually quite interesting objects. So it's like a really bright radio pulses. They are really short, coming from somewhere like out of our galaxy. And of course, this was a huge, oh, exciting, what is this discovery? But by now, we have quite a few ideas what they could be, and it's probably not aliens. But that's kind of an example. We don't have to, we don't have to make a special. I mean, you basically, with doing normal science, you can still look out for interesting effects.
Yeah, I think astronomy in general is sort of more. We would be happy to detect some kind of biosignature. We're not necessarily hoping to find like intelligent life right now, but like finding some kind of biosignature or something really simple would be really cool, which is partly why the story of the possible discovery of phosphine on Venus, or that's since been challenged, but when that was published, it was really exciting because it seemed like we might have found a biosignature.
Yeah.
Even though it wasn't intelligent life, but we were speculating, it was still exciting.
We got a question on Periscope just now, for you apparently, certainly not for me. Can you differentiate between the natural metallicity of dying stars as planetary objects fall into? Like say, artificial one that could be placed by a high... okay, I think the second one is related to extraterrestrial intelligence. Anyway, so the first question, I think, is referring to if you can detect that the metallicity of a star is like higher than it should be by all the planets that have fallen into it.
Oh, I see. So so the stars that we look at, they're called white dwarf stars. They are extremely dense, and they have very strong surface gravities. So if you just have a white dwarf in isolation, it will pull anything that's not hydrogen or helium below the part of the atmosphere that you can actually see. So in principle, a white dwarf just has a very, very pure hydrogen and helium atmosphere. And that makes it really, really easy to see if there's some pollution from some other source, because anything that's there that's not hydrogen or helium is pollution, because it must have arrived really recently. It can't be part of the original star, because if it was, it would sink down and you wouldn't see it, and that would happen very quickly. So for white dwarf stars, it's you can't really tell what the metallicity of the original star was directly, because you can't see any of the original metals. This is the idea, at least.
Okay, so you can't kind of figure out, oh, the star has lots of metals. Like, you can't see how much stuff has already fallen into it in the last, say, billion years, because it's all in the center. You can't see that, or is there a way to see this?
No, but well, there's ways that you can try to infer it. So there's a system where, I forget exactly the details of how they did this, but they figured that there was a lot more hydrogen in the atmosphere than you would actually expect there to be. So you expect there to be some hydrogen anyway for a white dwarf, but they figured out that there was more than you would expect. And they thought that that might be because it had been polluted by a lot of water. So that's H2O, so that's water. Water is made of hydrogen and oxygen. So the idea was that it's accreted a lot of water. The oxygen has all sunk through the atmosphere and you can't see that anymore. But the hydrogen is still there. It didn't sink because it's got a very low density. So from that, you can try to rewind and work out how much oxygen there was that's fallen into the atmosphere of this white dwarf, but has since sunk below the part that you can actually see. So
that's
there
interesting.
are ways
Yeah.
that you can try to figure this stuff out.
Okay. And the other question we got from YouTube was, can you see the Pleiades with the telescope of a commentator / a simple telescope, I guess. I have no idea what you need to see the Pleiades. Can you see it? I'm not sure. No idea.
I might be completely wrong, but my first one is, can you see those with the naked eye?
I'm a cosmologist.
Is it? This is an
yeah, sorry, I don't really know like what details you can see or how good you can see them with eyes or telescopes. Yeah.
I'm not sure I'm much help, to be honest, either. Sorry.
No worries, no worries. Okay, so we got the question about, say, an artificial one that is placed by high Kardashev scale civilization. So I think XFS on Telescope is commenting about some part of extraterrestrials that we were talking before, but I have no idea what the question is referring to. Maybe like to the fast radio bursts I mentioned. I don't think I don't think they were realistic for. I don't think there were any like really realistic kind of extraterrestrial models to explain those. Another question we got on YouTube was, what is interstellar dust? Do you want to say something about this, Andrew?
I guess it's kind of relevant to the field that I'm working in, actually. So the interstellar medium, or ISM for short, is just refers to whatever material is out there in between stars, or I guess you could say stellar systems. To we're not counting planets and that kind of thing. So there's some material that floats in between stars. I think it's pretty much just hydrogen and a bit of helium. Very sort of primitive material. It's relevant to the field of white dwarf pollution, because when people first discovered material polluting white dwarfs, one of the ideas that they had to explain it was maybe it's white dwarfs are like moving through this interstellar material and accreting that, and that's what's polluting the white dwarfs. That's since been ruled out because the composition isn't quite right, and also you would expect to see some correlation between the parts of the galaxy that we observe these white dwarfs to be in relation to where there's the most interstellar material, and there's no link between those two things as far as we can tell. So
are there big differences in the galaxy, kind of how much interstellar material there is? Like, are there more dusty regions and less dusty regions?
Well, I'm gonna say yes, but this is going a bit beyond
I mean, it would be surprising. It would be surprising if it would be the same, I suppose.
Yes, I believe there are. You'd have to ask somebody else who's more knowledgeable.
Oh yeah, sure.
Like exactly, how that varies throughout the galaxy. But I believe there are variations.
Okay, we got a few more questions now. How do we recognize if an exoplanet is geologically active? So I don't think we can recognize it for like planets outside of our solar system, or can we?
Well, there are some clues, I think, that you could use it. So I remember there was a really interesting talk that I saw once. I'm trying to remember the details of it because it was about a really interesting way that you can try to infer something about the surface, how reflective the surface is based on the observations that you make of it. I'm trying to remember how this works. I think the idea was there was a particular planet that this team was observing, and they deduced that it didn't have much atmosphere, and they worked that out because the hot spot of the planet, the hottest part of it, was pretty much directly below, or like it was the bit pointing straight at the star. And if there's an atmosphere, you get material moving around and circulating in the atmosphere. So the hottest point of the planet is not necessarily the part which is directly facing the star. So if those two things are the same, then they can deduce that there's no atmosphere. They then deduce that any light that we see from it has reflected directly off the surface. So that means that you can try to work out something about what the surface is made of. And this particular planet that they were talking about, I think that they concluded that how reflective it was matched roughly with basalt on Earth, which is a type of rock that is, what's the word? It's expelled from like the mid-ocean ridge, for example, in the Atlantic. So that's like a signature of tectonic activity and hence volcanism. I just find it really interesting that they were kind of able to make this chain of arguments that suggested that there might have been, it's a suggestion that there might be volcanism on that planet. You might also be able to work it out from atmospheric composition. So this is, again, not really like exactly my area, but like if you have volcanism, then that's going to propel a lot of the material from the interior of the planet into the atmosphere. And that changes the composition of the atmosphere. And you might be able to work out the signatures of volcanism from looking at the atmosphere, potentially. Yeah, I wish I could remember the name of this planet that had the potentially basaltic surface, because that's super interesting.
I can never remember the names of planets, but except for TRAPPIST, because I have a slide for this one. We got a follow-up question here, or I guess another question from this person on Periscope, not YouTube Periscope. We have this asteroid belt, and we have the kind of Kuiper belts, Oort cloud, etc. How common are those debris belts around other stars, so in kind of exoplanet systems? Do we have models for this, or do we have seen any?
I feel like this is something I should know more about than what I actually do know. I think I think that there is evidence for this based on this. Yeah, these are the images I was thinking of.
I'm not sure either, but basically for when kind of a star forms and its solar system just is forming, you have a disk with all the material that didn't make it into a star flying kind of around on a disk. And when you form a planet, the planet kind of goes in the circle and attracts all the dust in its orbit. This is kind of why you see those dark parts in the orbit. But the remaining parts, it doesn't form, all the dust that doesn't form planets, I think is what data forms all those belts, like the asteroid belt, the Kuiper belt, etc. So I would expect, like, I think theoretically, you would be expecting them basically everywhere, like, because there's always something left over.
Right.
But yeah, I'm not sure
It'll,
if we have or can observe them.
yeah, I'm not actually sure either. I think it's also perhaps worth mentioning, but it's not necessarily just whatever's, well, I guess it is kind of whatever's left over, but we might, like the asteroid belt might potentially have been sort of the remnants of some collision between
Yes.
planets that were forming very early on. So it's not just like that they've never been involved in planet formation. They might have been, or they might have started to form a planet but then been destroyed. Has it ever been observed? I'm gonna refrain from giving an answer because I'm worried that whatever I say is going to turn out to be wrong.
Oh no, don't worry. Like we don't know everything. But
No.
we'll try. We got a few more questions. Can you do a PhD at the university? A PhD in astronomy at the University of Cambridge or Oxford? Yes, you can at least in Cambridge you can, because that's what we two are doing.
Yeah.
I think you can do it so in Oxford as well.
Yes, it's not called a PhD though. It's called a DPhil in Oxford.
Oh dear. Okay.
But it might also be worth mentioning that there's different institutes, like different departments in Cambridge where you can do astronomy PhDs. So there's the Institute of Astronomy, and there's also the Cavendish, which I think does more sort of radio astronomy and that kind of thing.
Yeah, basically the physics institute that has a radio astronomy section. Yeah.
So yeah, if you're thinking of applying, then you should be aware that if my memory is correct, you make two separate applications, if I remember rightly, and you have two separate sort of application processes for the two different departments.
Okay, and a related question we got recently on Slido, our first Slido question today, is what is the difference between astronomy and cosmology? And that's, I guess, not that clear, but I would say usually what you would say cosmology is a subfield of astronomy. So astronomy is kind of dealing with everything, kind of stars and outer space, like galaxies, stars, the interstellar medium, galaxy clusters, but then also the larger scales cosmology, the cosmic microwave background, etc. So cosmology is kind of the special word to everything, people stuff that deals with very large scales, like things like the whole observable universe, or the large scale structure in the universe, or the cosmic microwave background that we can observe, and especially also very early parts of the universe. So the inflationary era, everything that was around the cosmic microwave background, and potentially even the first few billion years, where we cannot really do any practical astronomy in terms of observing stars, but kind of do simulations. And I think that is all what you would call cosmology. At some point, the boundaries get a bit, like, at some point, you're not sure if you should call something cosmology when it goes to kind of large galaxy clusters. You might observe them with an X-ray observatory and study them from this point of view, or you might observe them in the cosmic microwave background, and then you would count them more as cosmology. So the boundary isn't like straight cut. And I would call myself a cosmologist and an astronomer, and astrophysicist for that matter. So yeah, I think that was an agreeing nod.
Yeah.
So then we had, does planetary science come under astrophysics or Earth sciences? That's an interesting point. I think actually in our case, it's a bit of both. Yeah, actually, and I think one of our students is working in, or at least one of our professors is working combined with Earth sciences and astronomy, I think.
Yeah. Yes, and in fact, there's a couple of students which are sort of, I believe, spend time in both departments, because there's really, there's quite a lot of overlap at that point. And what I'm doing is also kind of an overlap. I mean, all the data that I work with is coming from observations of white dwarf stars. So this is very much in the field of astronomy. But then the modeling that I'm doing is all about planetary interiors. So that's really more related to Earth sciences. And yeah, so it's definitely like a grey area in the middle where you need knowledge from both fields.
Yeah. Okay, and while we're at the cosmology field, we got a question earlier. What is your topic of research in astronomy? I guess you explained it earlier, and I forgot to explain it, I suppose. I'm doing, well, I mentioned already doing kind of cosmology, and my subfield is what we call 21 centimeter cosmology, which is a word that doesn't tell you much if you don't know the field. But basically, the idea is between, if you look at kind of at the slide here, between the kind of the afterglow of the Big Bang, so the cosmic microwave background, so like a few 100,000 years after the Big Bang, and about 1 billion years after the Big Bang, or a few 100 million. There were no stars in the universe, and basically we call it the dark ages because you can't see anything with normal telescopes, and we did know very little about it until recently, and we still know quite little about it. But in the kind of recent years / next few years, we are getting the area where we actually can detect the signal of all the hydrogen in the universe. Basically because the cosmic microwave background, like the radiation from the Big Bang, goes through the universe through all the 13 point something billion years and comes towards us. And while it passes through this hydrogen, a billion years or so after the start, it leaves a small imprint on the signal. And we can now today basically look at this background signal and search for this imprint, which happens to be at a wavelength of 21 centimeter times some factor, which is why we call it 21 centimeter cosmology. And that's what I'm working on. So trying to figure out how did the universe look before we had stars, or how did the universe look in the kind of very early stages. Not very early in terms of the first billion years, not in terms of the first second. That's what other people do.
I think that sounds quite early.
And a related question, how do we know the age of the universe? That's actually a really interesting question. And there are a lot of different ways you can approach this. And by combining them, you can actually learn a lot. Surely, Andrew, you probably know a lot about how you can use the age of stars to kind of figure out, oh, those stars are really old. And the universe must be at least this old. No, don't you do that? Okay, anyway.
Well, it says the age of the universe. So the person I would think of would be like the movement of the galaxies.
Oh, okay.
Is that not? Should I not be
Oh,
thinking?
well, the one I thought about was basically I knew that many people, there were observations of stars, and they figured out, oh, the star is so old, like it must be alive for, or was it a white dwarf? I think it might be a white dwarf that's a cooling white dwarf. I'm not sure anymore what it was. An observation of either a star or a stellar remnant, and that was shown, oh, this must be 13 point something billion years old, and therefore the universe must be at least as old as well. I guess the more the kind of more straightforward answer or more accurate answer these days is using kind of those large-scale cosmological probes that I mentioned. So the cosmic microwave background, I have a nice image of this one, is what you see when you look at the sky and just look at the radio frequencies, basically. And basically, the whole sky is shining very faintly with a kind of temperature, you could say, with a signal that corresponds to a temperature of 2.7 Kelvin. But then, if you build a really nice satellite and measure this really in lots of details, you figure out that it's not 2.7 Kelvin everywhere, but it varies by like 0.0000 something Kelvin. I think maybe it was not too much, like by much less than 1%. So really tiny fraction, but we can measure this variation. And so the sky is hotter or colder at some places. And that's what you see on this map. So the red points are kind of hotter on the sky and the blue points are colder. And this tells you how the universe looked kind of very early on. And from this, you can basically calculate kind of how it evolves until today. You can combine this also with the various measurements from today. For example, you could look at all the galaxies in the universe and look at kind of the large-scale structure distribution, which should give you kind of a cosmic web. And yeah, lots of these cosmological probes you can combine. And I think currently the estimate is like 13.83 billion years for the age of the universe. Billion, yes. Okay. How do we know the age of a star? I think that's more your area than mine. Or well, maybe it's not none of us.
Yeah, well, I mean, I guess it kind of might depend on the type of star. So I mean, I can say something about white dwarfs for this because I think this is quite interesting. For white dwarfs, they don't have any. These are dead stars. They're just the dense cores of a star like the sun after it's run out of fuel to burn from fusion, and it just it sits there. It has no way of generating more energy. It doesn't have any fuel left to burn, so it just sits there getting colder and colder and colder over time. Which means that for these white dwarf stars, if you want to know how old it is, you can kind of use the temperature as a proxy, because the colder it is, the more time it's just been sitting there getting colder, and hence the older it is. For a main sequence star, so like the sun, I'm not quite sure. I'm not sure how you would. I feel like this is something that I did know at some point, but have since forgotten.
Yeah, I mean, they do know that the sun is like 5 billion years old, so there must be some way, I suppose. So basically, you have the star, and in the very early on, it's like burning hydrogen. It has very little helium, right? But the helium all falls to the core. So can you like detect this, like how much helium there is, maybe? Because the more helium a star has, the longer it would have lived. Not sure though if you can measure this. Okay, I'll ask the next stellar evolution person that's joining this live stream. Probably next week, by the way. I will make an announcement at the end.
As soon as this stream ends, I can tell. I'm going to remember. Oh yeah, that's how they figure it out. But that's how it is, I guess.
Okay, we got a few more philosophical questions about Marxism and scientific materialism, and I'm not confident about talking about these without googling the names, words first, unless you want to go into this. I would move this to first googling and then talking.
I am curious. I mean, I can't see what the questions are, but I am intrigued to know now that you've mentioned it. I don't know if I'll have anything to say.
Well, the question was, what is a cosmologist's view on Marxism, and what is scientific materialism? And okay, I'm not sure I can.
The second one.
Okay, go ahead.
Sort of. I mean, this is all based on. This is really not my area of expertise anymore. But I think materialism in a scientific context is just the idea that, if my understanding is correct, that the universe really just consists of physical objects, like particles and photons and that kind of thing. The idea is that there's no, I don't know, ethereal things like, I don't know, what would be a good example? Like a soul might potentially be a good example of something that is like immaterial. So a scientific materialist would probably say there's no such thing as a soul.
Ah, yes.
In the sort of immaterial, like depending on how you define soul, but this is going well beyond what I know about. I guess this is a kind of a philosophical question, and it's sort of different people will have their own opinions on this.
Yeah, trying to interpret this from the kind of Wikipedia introduction, it seems to be the idea that everything's kind of a physical thing, and you can actually use the scientific method on everything, and there's nothing that's like excluded from science.
Yeah, that's much better. That's much better than what I just said.
Well, I mean, I cheated, right? I googled. Well, I guess it's maybe not cheating.
No, that's good. That's better than just doing what I did and just saying whatever comes out of your mouth.
So you got a follow-up from the discussion about the kind of stellar debris around stellar systems and the thing where we didn't know what's going on. And the follow-up question is, can the size of the native star influence the size and quantity of planets around the star?
Oh, I think so, and this is another thing where I'm going to have to say that I wish I could remember what I'd read about this better. So it's definitely like an interesting field, like that. How does the properties of the host star relate to any planets that it has?
There are obvious effects, right? I mean, is there like an effect from the stellar wind, like affecting the planetary formation?
Sorry, does the effect from
Is there like an effect of the stellar wind that affects the planetary formation?
I
really have no idea about this.
I guess I think a stellar wind would probably only affect planets that happen to be like very close into the star, but potentially, in terms of ways that the star can affect a planet that's kind of already formed, you can get things like I think I might have said that UV radiation from a star can cause photoevaporation of a planet's atmosphere after it's formed. So you can form a planet with a big atmosphere, and then you have a star that's emitting a lot of UV radiation, then it can cause a lot of the atmosphere to kind of evaporate and just sort of float off into space, which I guess is going to affect the. Okay, this is relevant to the question actually, because that's going to reduce the radius of these planets, and also because this happens more often for, I'm going to say, low mass stars. I think that will give you some relationship between the star's radius and how massive a star is and the radius of the planets that orbit it. Yeah, I just think about what you said about stellar wind. Maybe that's relevant.
I mean, it's just what I came up with like now. Don't worry. We got a follow-up question actually about it said solar systems. Yeah, in solar systems, in extra solar systems, right? So in other systems that are not our own, which is more common, terrestrial planets or gas planets? And maybe a really interesting thing to say here is that we observe lots of gas giants. But the main reason why we do that is because we observe planets by seeing the star get darker, like by seeing a big object going in front of the star. And this is much easier to observe if you have a gas giant as opposed to a small terrestrial planet.
Yeah.
As an example, I have the TRAPPIST-1 system here, where we have found 7 planets, and all of them are really close to the star. And I'm not sure if they're all gas giants, but I'm pretty sure that many of them are, aren't they? Anyway,
if those sizes are to scale, then they're all too small to be gas giants.
Well, I wouldn't be sure if the sizes are to scale. Maybe they are. Anyway, what I wanted to say is that, right, so what we see here is like, all the planets are super close, and you might think, oh, is the solar system like an outlier with, being so large? But actually, if there were such large planet as like in our solar system, we wouldn't be able to see them in that solar system. We only can see stars, the planets, because they are so close, or that makes it at least much easier to see them. So that's also kind of an effect you have to worry about when you try to do the statistics. I do think
something else that maybe is worth mentioning as well is that there's other ways of discovering planets as well. So one thing you can do is look for transits when a planet goes in front of its star, and then the bigger the planet is, the easier that becomes. But also you can look for how a star will kind of wobble a little bit as it gets pulled by planets that are orbiting the star. But again, that is easier the bigger the planet is, because the bigger the planet, the more it's going to pull on the star. It's also possible to directly image some planets. Again, that's easier the bigger the planet is. So there's a common theme here, like it's much easier to detect the big planets. So it's kind of an open question at this point, whether they are actually more common than terrestrial planets or whether it's just observational bias.
Yeah. Okay.
Sorry, I interrupted you while you were going.
Oh no, it's fine. It's fine. I mean, that's the point, right? You're much more knowledgeable than me about planets. I mean, you're the expert.
I wouldn't say expert, but
okay. So let's get another of those. There was a really good question on periscope just now. And do all the isotopes of hydrogen have the same spectral absorption? And are they equally redshifted after the universe cooled down? So I talked about this. We find this 21 centimeter line of hydrogen everywhere in the universe, or we want to find it. And what I should add is this 21 centimeter is, when you take a hydrogen atom in the lab and look at it, then it will have this absorption line at 21 centimeter. And the reason is a hydrogen consists of a proton and an electron. And they can have either both the same spin or opposite spins. And the opposite spin variation is slightly energetically favored. It's favored by, I think, a few micro electron volts. So you need a little bit of energy to flip between the one and the other state. And that's what causes this absorption line. And this energy difference corresponds to this 21 centimeter. But now, the universe did, in fact, as XFS on Periscope correctly says, the universe cools down over time. So at the beginning, like, a few 100,000 years after the Big Bang, the universe is like a few thousand degrees Celsius or Kelvin hot. So it's really hot. And today, this kind of radiation that's arriving from there is only 2.7 Kelvin cold, so like really close to the absolute 0 point actually. So you have this big change. And in fact, when a hydrogen atom is very close to the, like very old, so let's say you have this Big Bang, and then the radiation passes the hydrogen atom only a few 100,000 years after the Big Bang, then you will get a dip at what is at the time 21 centimeter. But now this universe cools down, and we have this effect what we call redshift. So all the wavelengths, they expand, you could say, with the universe. So the wavelength goes from shorter to longer wavelengths. And what was 21 centimeter at the time might have been maybe 2 meters or 4 meters or something today. So we call this 21 centimeter cosmology, but actually we're much more interested in the longer wavelengths because that means older and more interesting signatures. So yes, the redshift kind of does happen, and that's why whenever, like, the time when you find this hydrogen determines what is the frequency that you actually see today. And the other question you asked about the isotopes. So there is hydrogen, which is, as it's just said, just a proton and an electron. But there's also deuterium, which is a proton and a neutron plus an electron. And I'm not 100% sure if the signal is the same. It might be, because basically it should. Okay, no, I'm really not that sure about this. This kind of so-called hyperfine transition is related to the spins of the hydrogen, and I do think that the neutron has a spin. Yeah, I mean, has a spin as well, and it probably influences this. So it's probably not the same, I would guess, if I had to guess. But also, deuterium is very, very, like, there's so much less deuterium than hydrogen in the universe, it makes a really small effect. So we will be happy if we can detect the hydrogen at all, and don't worry about the deuterium for now. One question we got a few times: does the size of gas giants fluctuate? I guess over time, or like kind of with temperature or something.
Yeah, I'm not quite sure if this is referring to like an individual gas giant that sort of changes over time, or whether it's just asking about like the different.
Well, I mean, do you want to answer both questions?
Okay. Okay. Well, I guess the easier question is the second one. Like, if it's asking like, do different gas giants have different sizes? Because the answer to that is yes, and we can see that in our own solar system. I mean, Jupiter and Saturn are not the same size, and we also have two.
Okay. It's probably the first question, because people in our chat seem to ask hard questions today.
Yeah, but it would be. Yeah, maybe it's too optimistic to think that it's a second question.
Okay. So what does the size depend on?
Oh, sorry.
What does the size depend on of the gas giant? Like, does it depend? I think it's just basically temperature and kind of the mass, right?
Yeah, I guess it will sort of depend on the composition more generally of.
Oh, right.
Yeah. There'll be a whole load of there's a whole load of like modeling that will go into answering these kinds of questions, like how does the assumed equation of state of your material, whatever you think it is, translate into a relation between like the total mass and the total radius. For a given, I was just thinking, like, what would cause the mass of a size of a gas giant to change? Because like, if you look at Jupiter, for example, it doesn't. I don't think it's really changing much. But Jupiter's like quite a long way from the sun. I was thinking, like, there's a lot of so-called hot Jupiters out there, which are planets which are similar to Jupiter but just much closer to their star. And I think it's at least plausible, I don't know if this is the case, that if when you're that close to your star, potentially the temperature is high enough that you can get quite a significant atmospheric escape, which is where, meaning that the planet is so hot that it can essentially just boil over time, and it's really kind of the same, a very similar process to like if you boil water in a saucepan, for example. Some of the molecules have enough energy that they can just escape.
Okay, so when you have a planet that's very hot, it will lose mass over time, and then it will, of course, change its size as well.
Yes, there might potentially be other processes that I can't think of off the top of my head, but I think yeah, if you have a hot Jupiter, I would suggest, I feel somewhat confident that it's at least plausible that their mass could decrease over time.
Okay. We got a few questions on YouTube from Astrox Physics that I didn't get to yet. If Betelgeuse exploded, how will we study it? I would say, I mean, it will be very bright. So, take a nice spectrograph and get a very nice detailed spectrum of a supernova would, I think, be one of the one of the first things I would do.
Yeah, I think people would definitely be looking to sort of get a spectrum of the supernova and try to work out what elements are in there.
Oh yeah.
They would look for, yeah, I guess either absorption or emission lines, whichever's relevant to this. That would correspond to elements that we think would be present in a supernova explosion. Because the idea is that when if you have a star that's gone supernova, the reason that would happen is because it's exhausted all of its fuel, and we think that as a star burns its fuel, it will create successively heavier and heavier elements all the way up to iron. So we expect that when a supernova happens, those elements will be released into the interstellar media. This ties it back to an earlier question. And yeah, but I think people would definitely be looking to see if we actually see elements in the explosion. They would definitely be looking for that. Probably a bunch of other things as well.
Oh yeah, I think one important one would be kind of the time evolution of the supernova. Like what happens first? Like, do you get a burst on the neutrinos first, or light first, or gamma rays first? And how does it change over time? Because we want to figure this out for far away supernova, and having one close by, I think, would be very interesting.
Yeah, actually, it might be non-obvious. Maybe it's worth talking a little bit more. But you mentioned that neutrinos might arrive before light, which is
yes, I should explain this.
That's potentially a bit confusing, but
yeah. So
I guess.
Do you want or should I?
I have a sort of a surface level knowledge that I could give. I don't know. You might know more, but
well, I'll just start and you correct me.
It's very. Okay, you go.
Yeah. So the kind of the matter around the supernova is very dense, and like basically when the photons that escape from there will take some time to get out of the supernova, like get out of all the material, and will have lots of scatterings and collisions. And will take, I'm not sure about the time exactly, it's like minutes, or is it longer?
I don't know.
Okay, but it will take quite a bit of time for them to get out of the supernova. And then the neutrinos that are also being created during the supernova, they scatter, like they interact much less than photons. So they will easily just pass through the material, or mostly, I suppose, and will reach Earth much sooner. So we could kind of measure the difference between those times.
Yeah.
And we want to add some more details, Andrew.
I guess you could potentially say that your neutrinos will travel slower than light.
Oh, yes, I
so
will.
Potentially, I mean, if the supernova was really far away, potentially the light could arrive first. I guess that's possible.
I think the difference is too small for this. Like the neutrino mass is like, super tiny. Like,
yeah, sure. But so, I mean, this is all dependent on like how soon. Like we think that neutrinos will escape the supernova before light does, by enough time that light can't catch up. But something that we would definitely look for if we did see a supernova would be like, if the light did arrive first before the neutrinos, that would tell us that something was wrong in the modeling, and there's neutrinos don't get the head start that we think that they do.
That's a good point.
Yeah, that's kind of what I'm.
Yeah, so the neutrino mass is about 0.1 electron volts, which is, I think, 10 to the what is an electron? It's an electron is in electron volts is like almost 1 mega electron volts, so it's like 10 to the minus 20 kilograms ish, in neutrino, maybe a bit less. I think that sounds right. And then comparing this to what's the energy of a typical neutrino? Could be much higher. Yeah, okay, it's hard to, I can't do the calculation in my head. I need a paper for this. But
Yeah, that sounded a bit
it would be
hard,
interesting
actually.
calculation. Like if you have a supernova at the end of the universe, at the opposite,
Mm.
at the kind of end of the observable universe, would the light overtake the neutrinos? Like what would be the difference?
That's an interesting question.
I'll calculate this after the stream. Does Betelgeuse have planets around it?
Ooh.
I didn't hear of any, and I suppose I would have heard.
Yeah, I'm not aware of any either.
Yeah, probably not. I think it would have been in the
We
news.
would say no, but this could just be ignorance on our part,
Yeah. Okay.
It'd be interesting if it did, because like, would they survive Betelgeuse exploding? I mean,
well, no.
well, depends how far away they are, right?
Oh, right. How is it in our solar system? Everything up until Mars, I think, would die with a star, right?
I think the current understanding is that everything up till Earth would be engulfed in the
Earth. Okay.
the red giant star that the sun would form. Earth itself is a bit of a question mark. Like, Mercury and Venus, you can wave goodbye to them. Mars should be all right. Earth, we don't quite know, actually. It's
I mean, it certainly will be really not nice on Earth.
Oh yeah, if you definitely want to get away before that happens.
Okay.
That's not going to be a fun time.
Do I have to go to Mars, or like do I have to go further away, like Saturn moons or something? I think Mars might get a bit hot.
I don't know. I suspect that Mars might get a bit toasty, but I don't know.
Okay. Other question we got here. A little out of topic. And can modified Newtonian mechanics explain gravitational lensing? And I'm actually not sure if there is a version of this theory that can explain this. So maybe I should explain this in a bit more detail. So our theory of gravity currently is a bit, problematic in that sense that we look at a galaxy and see, oh, it doesn't work. And we have to assume there is some hidden matter that we cannot see, which we call dark matter. So basically, every galaxy, actually, most of the universe, most of the matter in the universe, about, 80% or something, following our current understanding, is consisting of dark matter, which is kind of basically the same as normal matter, same as a table, just it's invisible.
You had a slide on this just now, which might be worth.
Sorry?
So you had a slide on this just now.
Yeah. Let me open the slide with the numbers, so I can actually give you the right numbers. Yeah. So if you kind of count the energy in the universe, 26.8% of the energy in the universe is dark matter. So if you just look at the matter, so comparing ordinary matter to dark matter, it's a bit over 80%. And basically, yeah, it is invisible. It doesn't interact with anything. So basically, you could just move your hand through dark matter. Dark matter can just fly through you. You can shine light through it. It just doesn't do anything as far. Like, we are trying to find out what it does, but currently we didn't find anything that interacts with dark matter or any kind of sign of dark matter, except for it's apparently there and curving our light, curving the rotation curves of galaxies, making structure form early in the universe. There are actually lots of kind of points that are all mostly solved by the existence of dark matter. So which is why the dark matter theory is very, very popular. Like we are quite sure that there's dark matter because it just solves so many problems. Like it's just, it's not that unplausible. And there are lots of hints that this is actually the case and there is this dark matter. But nonetheless, of course, people are looking into alternatives. And some people came up with the so-called modified Newtonian dynamics theory. And this is an idea of a different kind of law of gravity. So it's kind of basically Newton's law of gravity slightly modified. So it's not using Einstein's laws of gravity. And with this modification, it can work. For example, galaxy rotation curves would look the way they are without any dark matter. But then you also have to explain everything else that shows hints of dark matter. So you have to explain how gravitational lensing works. So basically, lensing is when you have a massive galaxy somewhere, or a bunch of matter, and light flies past it. This matter curves space-time and also curves this path of the light, which shouldn't happen without general relativity. So in this Mond theory, which is how it's referred to, you also have to explain this in some way. And I'm not sure if they can. I read recently that there was an approach of how to explain the structure formation, so one of the other signs of dark matter with modified gravity, but I'm not sure if lensing is already explained. It's quite hard to do, I think. Yeah, we just got a note about our escape plan for the solar system. So Enceladus, one of Saturn's moons, is apparently a good target for fleeing to once the sun turns into a red giant. And I think it does have like ice, so it has like water, which means when the sun goes, gets a bit toasty, it might actually. I didn't do the math, but maybe XLS did the math or looked it up, and maybe the water turns into liquid water, or at least something. I mean, ice would be already nice. If you have a toasty sun, you could use some ice to make drinking water or something. Yeah, I think
maybe,
some of the moons would truly be a good point for refuge for humanity if we are still there in 5 billion years and didn't, go to other planets. I do think I have to bring up the.
I'll bear that in mind for 5 billion years time.
Yeah, I think I'd like Kepler 16b or something. Which one would be your favorite exoplanet to travel to? Before the sun goes supernova.
I mean, I wouldn't be too fussy if I had the chance.
You take them all.
What would be? It'd be quite cool to go to this one, which might have an entirely basalt surface, although if it has no atmosphere, that might be difficult.
Okay.
I'll go Kepler 16b as well. That'd be really cool.
Okay. Back to questions. What was it else? How is ice formed inside comets? That's a good question. I'm not sure.
Yeah, well, I mean,
where does the water come from?
So, well, my understanding of this is that when you have some disk that form, when you're forming forming material in a protoplanetary disk really early on in the solar system's life, you will have a whole bunch of different elements there, including oxygen and hydrogen, which is what you need to make water and water ice. Now, oxygen is quite volatile, meaning that it has quite a low condensation temperature. So if you get too close to the sun, the oxygen is all going to be it's all going to be gaseous. It's not going to condense into whatever body you're forming, like a comet or a planet.
Mm-hmm.
If you go far enough away, then you'll have enough oxygen there. It's cold enough that the oxygen can actually condense, and I guess.
So you get liquid oxygen.
Then you could. Well, I guess.
Or frozen.
React with whatever stuff is around it.
Mm-hmm.
I think.
Oh yeah, sure.
So you could get things like carbon monoxide, for example, if you have carbon as well. I guess if you have hydrogen, which you probably do because hydrogen is like everywhere in the universe, then you could. I think it would be as simple as you just have to be far enough away from the star, and then oxygen plus hydrogen condensing, you could get water. I might be horrendously oversimplifying that. I'm sure there are people who work on this who would be like, no, there's way more going on than that. But that's my understanding, is that you just have to be far enough away from the star.
Okay. Yeah, and then I guess you collect, like, when the comet forms. Was it a comet? I think we're talking about comets. Yeah, right. When the comet forms, there will be just this water, and of course it will like form ice because it's cold. Like it's truly below 0 degrees Celsius, and then yeah, you have the ice inside, and you get the all the fancy pictures and evaporation and tails because the asteroids are coming close to the sun, where it's much hotter than they're used to, and everything that is like solid evaporates.
Yeah, something that I find quite interesting about comets is that the tail of the comet isn't really a tail; it always just points away from the sun.
It has two tails, right? Or like it could kind of in theory.
Well, as in one pointing away from the sun and one pointing sort of behind where it came from.
Yeah, I think that's like it has like. Well, I mean, I heard
it
it in.
Much brighter.
Oh yeah, I think the tail that's pointing away is much brighter. Right, I think it's much brighter. So yeah, basically we should explain this maybe. Yeah, go ahead and explain why you would get tails, or why the tail would point away from the sun and not as a normal tail of stuff that's falling down from something behind, like in the path of the object.
Well, why does this happen? I guess it.
I guess is it solar wind, or is it like solar radiation pressure or solar wind or something?
I was just thinking about that. I think it would be solar radiation pressure. So, yeah. So the way this would work, I think I'm getting this. I hope I'm getting this right. If you have some particle that's just been released from a comet, it can absorb a photon from the sun and then re-emit it in any random direction, and that creates a sort of a net. If you have enough particles all doing this process, there's going to be a net momentum exchange from the sun's photons that it's emitting into the material, and the momentum is going to be away from the sun.
So in simpler words, when you have a cloud of comet dust and you bombard it with thousands of photons in one direction, it will start moving in one direction.
That's
in that direction.
Yes, I think that's maybe a better way of that's
the non-physicist way of explaining it.
Well, yeah, I mean, I hope that what I said is actually right.
I think it is. It's the same explanation I knew. Okay. I think.
Well, yeah, two of us can't possibly be wrong. For avoidance of doubt, that was completely sarcastic.
Okay. Yeah. So then, basically, you have this pressure or this movement in this one direction. So basically, you have your comet will lose material. For example, there's ice that evaporates into gas, and then this gas gets accelerated, gets pulled away from the let's say you have a comet here, you have the sun here. The radiation from the sun will go towards the comet and create a tail away from the sun. So even when the comet is like flying past the sun, it will have a tail that's pointing away from the sun, which consists of all the stuff that is moved by the sun's radiation. And I think you could have, or you usually do have, I'm not that sure about it, you could also have normal tail of heavier things like dust particles or rocks or something that are too heavy to be blown away by the sun's light. That will just kind of be in the path of the comet. So that will like be in the kind of normal traditional tail direction. Right, we got one note. So is it possible for a terrestrial planet to form far enough from the sun that it survives a supernova? Okay, so one thing I wanted to note, the sun will not go supernova. I said this earlier, I said supernova, but of course sun will go into red giant, but not a supernova. In general, I guess you have to distinguish between, does a planet survive, like as a clump of rock that's lying there, or does a civilization living on this planet survive? Because I think those might be very different things.
I suspect that a civilization on the planet is probably
you mean
a bad
lost
situation.
Yeah, I think some of us are really, really strong. Like, do they? I think it's like something like more light than this, like more energy than the star emitted all its whole life or something.
Yeah, I think that's about right. Yeah, but when a star goes supernova, the amount of light it emits in that one explosion is about equal to the total amount of light that it emitted over its whole lifetime, which could be like tens of millions of years for some, maybe hundreds of millions of years for some of these stars potentially.
Okay.
Depending.
So it's going to be a lot of variation. So certainly all the surfaces of all the planets that are anywhere close by will be anywhere the solar system will be completely fried, and especially the atmospheres as well. And I'm not sure if let's say you could hide on the back of the planet somewhere. I'm not sure if you could kind of in the shadow of the supernova, or if too much radiation would even go through the planet, like I don't know, say gamma radiation. Not sure if that's. I'm not sure about those details.
Yeah,
let's plan this in a few billion years. Let's put it on my to-do list. In 4 billion.
My intuition would be that a supernova is so powerful that I'm
Oh, you
not
mean
sure
it would destroy the
if being on the
planets?
other side of a planet would help you. But I could be wrong. I don't really know.
Yeah, I
I'm
mean,
not sure how helpful intuition is with this, to be honest.
yeah, I mean, supernovas, they make pressure waves that disrupt star formation in the entire region. So they might actually, at least in the early universe, I think they do this. Anyway, I think this might have they might be really strong and they might just destroy everything.
Yeah. If the planet was able to survive that in terms of like the material strength, you also have to bear in mind that the supernova would lose a whole load of mass. So even if the planet was still intact, it might not be bound to the system anymore. It might just sort of drift out into space. I don't know if that would count as surviving exactly, but that's potentially something else that could happen.
Yeah. Okay, one final question before we stop. We just got one on Periscope. Can a terrestrial planet be formed far from a star? Do you know, do we have any theories or observations? Is there any limit of how far away you can form a star?
You mean how far from a star you can form?
Yes, how far away from a star?
Yeah, I mean, some of these images are sort of the only thing that I could really point to. I mean, it's really, I guess you don't really have any observations that would tell us, like, because we mentioned before how difficult it is, like, to find terrestrial planets, even in the best case. But if you're looking for a terrestrial planet that's really far away from the star, then
yeah, I think we have no really chance in the near future to observe any of those. But kind of theoretically, I guess, I mean, there's like, basically, your guess only goes out so far from the star. Like, there's a certain limit. But I'm not sure what that limit is and how far away it can be. Like, Pluto is really far away. And, there's a Kuiper belt. There could be planets. Like, they could have formed the planet, maybe.
Given that Pluto exists so far from the sun, I think it seems plausible that you could maybe get something bigger than Pluto in a similar part of the solar system. I think we just don't really know about this. I could be wrong. Maybe someone's looked at this, but I'm not sure what the outer limit is on how far you could form a planet from the sun.
Let's ask some of the simulation people on this in the next one. And now that we're here, I should announce next week. That's a planned date anyway. I will do a special edition of this live stream with lots of people. So we'll do kind of the party edition, and we'll have maybe 5 or 6 people here, kind of mixed from all the areas, so that we're actually able to answer to cover kind of everything. Let's try this. So get us your best questions for next week, and we'll see if we can answer everything. Yes, I will announce it on Twitter and on the YouTube channel, etc. Most likely next week, next Monday, same time as usual. Great. Thank you all for watching. Thank you all for sending us the many questions. Thank you, Andrew, for being here and taking all the questions that I have no idea about.
That's all right. Thanks for having me.
And everyone, have a nice evening or a nice day, whatever, depending on your time zone. And see you next week.